Hi everybody, welcome to another video in linear algebra, section 6.1, inner product, length, and orthogonality. Inner product, dot product, I'm sure you see dot product before, but this time we define a little bit differently. If u and v are vectors in Rn, then we view u and v as an n by 1 matrices. Just the way we write the vector here. The number u transpose times v is called an inner product of u and v, and is often written as u dot v. This inner product is also referred to as the dot product. Okay. So a few things here. This is just one of the inner product. So it is not the inner product. And we will revisit later. The vectors doesn't have to be written in the column form. As a lot of calculation in this section or this chapter, we'll see that it is more convenient if we write a vector as a row. But I mean, not as a row, something like this. So there are a lot of different notation for vector. We can use the column vector. We can use just like a point, parentheses, a lot of coordinates. And besides, we learned in chapter 4 that when we talk about vector space, it doesn't have to be vectors. It could be polynomial, continuous function, matrices, a lot of things. Mostly, we think a vector is something with a few more than one component. Like here we have more component. As long as we can organize those components as a list or something, we can call that a vector in the vector space. All right. Now the way we define that, the notation is with a dot, so that's why we call this as a dot product or the scalar product, because the product here gives us a number. So we have a vector. If it is a column, when we transpose that become a row, and we have a vector. So the reason we write like this, so we can say this is the product of two matrices, one row and column, because from 1 to n, and this one one row, n row, one column, and when we multiply them we have just 1 by 1, which is just a number. Right. So let's look at the first example for the dot product of u and v. So the dot product is equal to u, the first vector is transpose, so just going to write that first and then we apply. So this u transpose v, so 2, -5, and 1 times 3, 2, -3. So first with the first, second with the second, the third with the third. Right. 2 times 3 plus minus 5 times 2 plus 1 times -3. And so we have 6 minus 10 minus 3, so minus 13 plus 6 minus 13 plus 6 minus 7. Right. So simple enough. Now we could see the vector like this. Like I said, as long as we have a way to organize the vector, there's a lot of different ways to write vectors. So let's just say notation of vectors. By the way, in most of the video on the textbook, we use the boldface for the vector u, but we could see an arrow on the top of u, And when we can see the vector, let's say I'm just going to say 3 component, right? We could write like that, or we could write in the bracket notation. Let's just write equal because they are equal. And then we can just write 1, 2, and 3. I said 3 component. That is a vector. That is a vector. A pawn can be thought as a vector as well. And then when we can write 1i plus 2j, this is more like when we see it in the physics or in calculus book. Usually we see in this notation where the ijk here will obtain as equivalent to the standard basis E1, E2, and E3. And of course the E1, E2, E3 is the standard basis come from the identity matrix. So E1 is 1, 0, 0, E2 is 1, 0, 1, 0, and E3 is 0, 0, 1. Yeah, so we can write vector in a lot of different ways. Of course, for each one you can write an arrow on ijk too. Because in this section on this chapter we use a lot of calculation with vectors, so it is more convenient to just write that horizontal, so it takes less space because usually we write in a row. Right, so in that case when we say u dot v just multiply the first with the first, second with second, third with third, fourth with fourth, and then add all of them up. Right, so that is 0, 9, 29, and 3, 32. Right. Of course, here we can just do by hand, but I just want to show that what if we need a calculator when things get more complicated, we can do this. Hit second, the parentheses. So what we do here is we use a list 1, 3, comma, -3, comma 5. So we just have a list of 4 numbers. So it looks like that. And then just multiply. By the way, this is just multiply pawnwise multiplication, so it's not going to give us the dot product right away. We have to do one more thing with it. Of course, we can just enter that in the u transpose v, enter that in the calculator. That will take care of everything. But here I can enter that. We have a list. And then we go second stat, I think, because now we work with the list. And then second stat, go to math, option number 5, and we're just going to add all of this up. We just hit second answer. Okay, we add everything on the last stat, and we have 32. Of course, we don't have to do that. This is simple enough. We just do it by hand. Just want to show you that on the calculator. When we enter the list or the vectors or of numbers, or we can just do it like that and then multiply, but then they just multiply the first with the first, second with the second. They don't add them up, so we have to add them up manually. Right, so next we have this here. Let u, v, w be vectors in Rn, and let c be a scalar, which is a real number. Then the dot product is commutative. And this is distribution and associated with the scalar multiplication. And then the gradient equal to 0 by when we dot product with itself, and is equal to 0 if and only if it is a 0 vector. Right. So I did mention before, this is just one of the inner product. What if we have, instead of vectors in Rn, we have polynomials, for example, how do we define a dot product between two polynomials or continuous function or matrices? There have to be some different way to define those things. And so when we define those things, whatever the inner product is, I have to satisfy these properties. So this theorem is for the properties of the dot product, but later on we use this as a definition. Anything that satisfies this condition can be referred to as the inner product in the vector space, and in that vector space could be polynomial, matrices, continuous function, or other things. Like I said, vectors is not always vectors. Right. Now the length of vectors. Now associated to the dot product, we have the norm. So the norm is defined based from the dot product, and the norm is equal to the square root of the dot product of itself, and equal to that. And the notation for the norm or the length is 2 bars. A vector whose length is 1 is called a unit vector. It's important, we will see that a lot. A unit vector is length equal to 1, and the process of creating a u from v is called normalizing v, and u is in the same direction as v. So we have a vector that direction. Now if we scale this down so that the length is equal to 1 and is still pointing in the same direction, then we call u is the unit vector of v. The process of finding vector u pointing in the same direction as v and the length is 1 is called the normalizing vector v. Right. And we have the properties of the norm or the length. Remember, the length is it satisfies every sense of a length or as a measurement. It cannot be negative. So when we have a constant multiplied to it, a constant could be negative. So when we move outside, we have to put absolute values to guarantee that the length is always greater than or equal to 0. Right. Now you see, for the rest of the chapter, we write the vector with the very loose notation. We could see like the notation of a point. Then we think that is a vector, because after all, a vector is a point and a point is a vector. If we just move the vector to the standard position where the end point is, where the tail is at the origin, then the head will be characterized by 1 point. So that vector is the same as this point. Right. Next, I'll find the unit vector in the same direction as v. Right. So we have v is that, and the unit vector in the same direction as v is given by vector v divided by the length of the vector v, and the length or the norm of vector v is equal to square root of the dot product of v by itself. Right. We'll see why we define that way in a minute. Right. So we just do that. Now we see when we write a vector like this, is more convenient than use the column. It would take a lot more space. Right, so we have, I said we use the notation for vector very loose. I used to write vector using the triangular bracket. This is more consistent with the calculus book. We usually use the triangular bracket. Of course, you can use the parentheses, or if you want to write IJK, like I think physics use that a lot more. Anyway, square root of the dot product of v by itself, so we just have 1, negative 2, 2 and 0, dot with itself 1, negative 2, 2 and 0. dot product, the first times the first plus the second times the second, and then so on. So 1 times 1 is 1 square, negative 2 square, and then 2 square, 0 square is 0. So we just have the vector, which is 1, negative 2, 2 and 0, and that 4 and 4 and 1 is 9, square root of 9 is 3. So we just divide everything by 3. So the unit vector in the same direction is v, given by 1/3, negative 2/3, and 2/3. 0 divided by 3 is still 0. Right, so that's what we have. Now, let W be a subspace of R2 spanned by X, 3 and 5. Find a unit vector that is the basis for W. So pretty much like I said, we have a very long vector or very short. We just normalize that to the length 1. In that case, we just divide by the length. So we have U equal to vector X divided by the length of vector X, with the note by 2 bars. Some books they just use 1 bar, but we use that for different things. We use that for absolute values. Sometimes we use that for determinant, and now it will be confusing if we use that for the length. So try something else, just 2 bars. X dot X. And 5. Yeah, like I said, don't get hung up with the notation. Just something that denote that we have a bunch of components. Some way to organize them is fine. Bracket, parentheses, in vector form in the column, doesn't matter. Right, that 25 and 9, that should be 34. Square root of 34. So we'll write as 3 over square root of 34, 5 over square root of 34. Right, so that is the unit vector in the direction of that vector, and that should be, of course, any vector pointing in the same direction. If there's only one vector, that certainly would be a basis spanned by the vector itself. Right, so what we have so far, the inner product. Now we define the length. Now we define the distance. For U and V in Rn, the distance between U and V, written as distance of U and V, is the length of the vector U and V. That is, distance of U and V is equal to the difference of U and V, and then we take the magnitude. We use the word magnitude here. No, but sometimes we can just use the magnitude. Which we use a lot with the conventional vectors like geometric 1. Right, now compute the distance between U and V. Of course, we have 2 points, just subtract them, right? That should be easy. Subtract them and take the norm, or the length, or the distance. I mean, the norm, the length, or the magnitude of the difference. So distance of U and V is equal to the length of the difference. So we have 7 and 1 minus 3 and 2. And give us what? 4 and minus 1. Right? Just subtract the vectors, and then the magnitude or the length is square root of the dot product by itself. Four square plus -1 square, that's square root of 17. Right, now we find the distance between u and v. Where u and v are vectors in R3 because they have 3 components. So pretty much we have this, and that would be subtract of the 2 vector u1 minus v1, u2 minus v2, and u3 minus v3, and that equal to square root of u2 minus v2, u3 minus v3 dot to itself. Of course, then we just have u1 minus v1 square, u2 minus v2 square, and u3 minus v3 square. Of course, that is just a distance formula that we have before. Of course, the distance formula comes from the Pythagorean theorem, so that's why when we find the length, I'm just going to do the simple case where v has 2 components, v1 and v2. Then the length is just have v1 here and v2 there. And Pythagorean theorem, it's just square root of v1 square plus v2 square. So we have that distance, and the hypotenuse is equal to the square root of the sum of the square of the legs. Right. I said there's nothing new. Right, the vectors u and v are in Rn. They are orthogonal to each other if the dot product is equal to a 0 number. This is 0 number because after all this is a scalar product. Right? We call that the scalar product. So the product is going to be a number. And then the Pythagorean theorem, what we mentioned before. 2 vectors are orthogonal if and only if they satisfy these properties. But this is kind of more difficult to verify. Verified by the inner product is a lot easier than using this to verify the orthogonality. But so we have the vector u and v. Then by the parallelogram method, u plus v is going to be the diagonal. With the length is equal to this diagonal, which will form a right triangle, and hypotenuse square is equal to the square. So pretty much a square plus b square equal to c square. So that is like use the length of u square, the length of v square add together equal to the length of u plus v square. So that's what we have. Definition: orthogonal complements. If vector z is orthogonal to every vector in W, then z is said to be orthogonal to W. The set of all z are orthogonal to W is called orthogonal complement of W and is denoted by W perpendicular or W perp. Now, Here says an example to that. Let W be a plane through the origin in R3. So W is a plane, so therefore they need two vectors for the basis, two-dimensional object, because a plane is two-dimensional object. And let L be a line through the origin and perpendicular to W. Then Z and W are non-zero vectors. Z's in L and W's on the vectors, the subspace W. Then the line segment from 0 to Z is perpendicular to the line segment from 0 to W. And each vector is orthogonal to, in L is orthogonal to W. Well, that's a lot of work. Just easier just try to put in. Now we have R3, three-dimensional space. Let's say in that we have a plane. And this length is W. And with that we have the line that is perpendicular to every line. We should say if there's a line that is orthogonal to every vector on the plane. So there's we have a line L. So here we might have a vector on L, just that this vector, let's say this vector Z. And then we have a little vector that is on W, maybe. Of course, a vector I can move anywhere on W. So I can move vector here. Let's say that is a little W, but of course we can move the vector too, right? So that is the vector W move from here to there. And we say that L is the line that is perpendicular to every vector in W. So we can draw that is Z. Vector Z is orthogonal to every vector on W, and every vector on W is orthogonal to every vector on Z. In that case, we say L is W perpendicular, or W is equal to L perpendicular. So we draw the line. Of course, the way we define as perpendicular is something I think in the plane, but orthogonal could be something like that. And one thing that we haven't mentioned, a little subtle about the orthogonal. Okay. One thing we have mentioned in orthogonal, if one of the vector is 0, then the dot product is always 0, right? So in that case, a 0 vector is by definition is orthogonal to all the vectors, because the dot product equal to 0, right? Just by definition. That's the way we define it, right? Vector x is in W perpendicular if and only if x is orthogonal to every vector in the set that span W, because we mentioned that every vector, let's say this is vector y, because we can move here, and that also perpendicular, Z also perpendicular to y, and W perpendicular is also the subspace of Rn, because that line obviously is in three-dimensional space, right? Now this theorem, let A be an n by n matrix. The orthogonal complement of the row space of A is the null space of A. So, and the orthogonal complement of the complement space is the null space of A transpose. So that's what we have here. For the matrix A, to find a row space is where we do the reduced row echelon form and take every row that has the pivot on it, and that gives us some space, give us the basis for those space. Let's say if we do the reduced row echelon form and we end up with something like this. In that case, this will will be the basis for row space of A. So these are the basis for rows space of A, defined by those two vectors. I mean spanned by those two vectors. And then the complement, when we solve for it, the null space, as you see, there will be one free variable. So this is it is one-dimensional object as opposed to two-dimensional object for the row space of A. So the row space will have dimension of 2, and the null space is the null space has dimension of 1 because they have one free variable. Of course, we can verify that they are orthogonal to each other too. Right, more sample here. Let U be that and V be that vectors. Find the inner product U and V. So this is all obviously just straight up from the definition. U dot V is equal to 2, 3, and negative 5 dot 3, 0, and 1. So first with the first, second with the second, and the last one with the last one. 6, 0 minus 5 is 1. Right. Next, find the distance between U and V. Distance between U and V, because we just find the length of the difference. So U minus V is equal to the distance of U and V. Two, 3, and negative 5. Subtract 3, 0, and 1. So we have 2 minus 3 is minus 1. 3 minus 0. And minus 5 minus 1. And of course, when we do that, we just, of course, we can take the dot product of this 7 and the square root, or we just say using Pythagorean theorem. So we have 9, 36, and 1, so that's like 46. Right, 36 and 9 is 45, and 1, 46. Right. So that is the distance between two vectors. Now we have the angle between two vectors is defined by this. Of course, this is, we already know this in pre-calc. If we have two vectors, and we define the angle between them, theta, then the dot product is equal to the product of the magnitude times cosine of the angle between them. Now if we want to find the angle between them, we just divide by the product here on the other side and take the cosine inverse. Right, so that's simple enough. So we say from here we can say cosine of theta is equal to the dot product over the product of the magnitude since we don't have the particular number, we're just going to write like that, and so theta is equal to cosine inverse. Right. Right. Let U and V be those two vectors. The area parallelogram is formed by vector U and V. It should be vector U and vector V. Is, of course, is that. Of course, we talked about this back in chapter 1, I think. So we talk about the area a parallelogram. This one vector. The other vector. And the area of the parallelogram is given by the length times height, pretty much, but the height is equal to opposite times sine of this angle, right? So that gives us the height, and the height times the base gives us the area of parallelogram. So v sine, u sine theta is the height, and the area is h, the length of h times the length of v, and the length of h is given by u, the length of u times sine of theta. So pretty much what we do is find the area formed by two vectors u and v. We're just gonna take the dot product, right? Because this is just a dot product. So we can say the area parallelogram formed by u and v by u and v. Let's put with the u like that. Will be equal to, of course, u v times sine theta, right? How's that relate to the dot product? Well, the dot product is cosine, too bad. So how do we relate the sine cosine? By the way, of course, when we have sine and cosine, and they're related by the Pythagorean identity, right? So cosine square plus sine square is equal to 1, right? Now, if we have cosine, we want to go from sine to cosine, because we just move 1 to the other side. Let's move cosine square. So sine square and then we take the square root on both sides, which is sine of theta equal to plus or minus square root of 1 minus cosine square theta. Right. Actually, we're just gonna, yeah. And then the nice thing about this is what? Is when the area, so we're just going to be worry about the positive case. So we just have the square root of that. Right. And so pretty much we can find the angle between two vectors. And then we just do that. We go to sine, and then from sine go back to that. Right. So cosine of the angle between two vectors my point is we don't need to find the exact theta. We just go from cosine to cosine by that formula. So u, that for u and v, 1, 2, 0, 2, 0, negative 3, square root of 1 square plus 2 square plus 0 square and 2 square plus 0 square plus negative 3 square. Right. So what we have is 1 times 2 is, I just want to spell it out, 2 2 times 0 is 0, and 0 times negative 3 is 0. So that's pretty much just 2 on the top, right? 2, 0, and 0. Right. At the bottom we have the magnitudes of u, square root of 1 plus 4, so square root of 5. And then we have that 4 and 9 square root of 14. So that is cosine. So give us sine equal to sine equal to 1 minus cosine squared. 5 times 14 is 70. Cosine square. Right. And we just do that. So the area equal to u v, and then sine is just that, 4 over 70. And we have square root of the length of u is square root of 5, square root of 14, times square root of 1 minus 4 over 70. Of course, we can simplify the math, but I said we can have the angle between two vectors, calculate by that, and then we can find the sine, go from sine to cosine, we have that. The nice properties is when we put all together, the dot product equal to the product of the magnitude times the cosine of the angle between them. Right, now square both sides. And that gives us cosine is 1 minus sine square. And multiply by 1 and multiply by sine. Now we put things together. And I'm going to put this by the way, this of course is taught as the area of the parallelogram with what we have earlier. Of course we can just use this. However, another for special case for R3, meaning vector in R3, only for R3, if it is higher dimension or less, it's not going to work. Only for R3, this is defined as a cross product. So you have u cross v, cross product with the magnitude, magnitude of the cross product square, subtract so we square the dot product equal to the product of the square of the magnitudes, subtract the cross product, the magnitude of the cross product square. By the way, this only works for vector in R3. Of course, we not cover. I don't think we learn about cross product in this class, so that might come in handy later. Right. By the way, the way we use parallelogram earlier is that it is only in R2, the vectors in R2. If you go back in section in chapter 1 where we learned about the area parallelogram, it is not like this. It is about the vector in R2. Right. Now let's see and D be those two vectors. Find a unit vector of U in the direction of C. Well, that's easy. So we want the unit vector of U represent the direction V of C. To take the vector divide by the length of the vector itself. The vector, let's just write in this notation, so we take less space, and then we have the magnitudes of that. Right, all we do is just find using Pythagorean theorem. We have 4/3 square -1 square. So the magnitude or the length of the vector can be either we use Pythagorean theorem or just take the dot product of itself like I did earlier. Earlier I just used the dot product by itself. But of course we can just jump straight into that. And that gives us, I'm just going to say it, 4/3 plus -1 square, or just 1 square, or just 1, and 2/3. Make sure you put them in the parentheses because the square apply to the whole thing. So this will be a fraction 29/9. And square root of 29/9 is square root of 29/3. Divide fraction is multiply reciprocal. So flip 3 square of 29. And so we multiply the 3 inside, we have 2 and 3 cancel, 4/29. Square root of 29. And -1 times that should be just -3 over square root of 29. And 2 and 3 cancel, we have 2 over square root of 29. Right. Next, so that D is orthogonal to C. So we just use the definition. We just find the dot product of C and D. If the dot product equal to a zero number, then they are orthogonal to each other. Right, so that's simple enough, straightforward. 4/3, -1, and 2/3. Dot with this vector 5, 6, and -1. So dot product 4/3 times 5 plus -1 times 6 plus 2/3 times -1. So 20/3 minus 6 minus 2/3. Right, 20/3 is 6 and 2/3, so of course that equal to 0. 6 is 18/3, and -18 -2/3, so that's -20/3, which cancel with that. So since the dot product is equal to 0, so we say C is orthogonal to D. So we just say C is orthogonal to D. Right. And so since C is orthogonal to D, C is orthogonal to any into the spaces spanned by D. So since we can write like this, since C is orthogonal to D, or D orthogonal to C, D orthogonal to the space spanned by vector C, and U, since U is pointing the same direction as C, so U is in that space. And of course, U is in that space spanned by C, so D is orthogonal to U. Right. So not much, not new material that we learn in here. Most of this come from pre-calculus. The only thing that different here is, of course, we can extend this into a vector. So of course, could be more than just three-dimensional vector space. Could be a lot to go with that. And of course, we have this nice theorem. But other than that, that's all we want from this section 6.1. As always, thank you for watching and see you in another video in linear algebra.